أيها الحفل الكريم، ننتقل الآن للمحاضرة العلمية الثانية بعنوان المختبرات الطبية والذكاء الاصطناعي من علم الأمراض الرقمي إلى التنبؤ بالأمراض ودعم القرار السريري. يقدمها الدكتور محسن بلال، أستاذ مشارك ورئيس مجموعة أبحاث الذكاء الاصطناعي والأنظمة المعقدة بجامعة الأمير سلطان بن عبد العزيز، ويشغل منصب زميل بحث شرفي بجامعة واريك في المملكة المتحدة.
Assalamu alaikum wa rahmatullah. Thank you very much for the very kind invitation and the kind introduction. Thank you to Dr. Yusuf for the first lecture. It set a stage very well that I can talk about little quickly, as well as a little bit of advancements in digital diagnostics through AI. So over a long time, we have considered pathology or histopathology as the science of what microscope could show and what a human eye could interpret. And nowadays, it is becoming a science of what data can reveal. So from pathology to predictions is the core of my talk, which is actually a story of how digital pathology and artificial intelligence have come together over a decade now to enable us with what we call as data-driven diagnostics. So they can not only predict based on what is visually apparent to something which might be not visually visible for a human eye. For example, diagnosis, risk prediction, and subtype prediction, prognosis, or even molecular alterations. So in my talk today, I will share a couple of case studies that we have been conducting for long, maybe 5 to 6 years at different countries, now in Saudi Arabia very recently, that how this shift has been enabling the data-driven diagnostics. So this is a bit of a disclosure. I have been working with University of Warwick from 2019 to 22. A couple of my case studies belong to that research and a couple new one as well. So I also do not have any other conflict of interest to declare. So a little bit quick I will go because the time is running short. So multi-gigapixel whole slide images are the center of this data-driven transformation in diagnostics. So these are biopsies or glass slides which are digitized as a first step. And then we have a very high resolution whole slide images which can be input to the computers and they can then analyze these images. So in my talk today, there are 2 case studies from the colorectal cancer. In the first, we have developed pre-screening AI, which we call as COBE pre-screening, colon biopsy pre-screening. This was a study between University of Warwick and University Hospitals of Coventry and Warwickshire, with a couple of hospitals from the UK and Portugal. They've given us their data for the validation as well. Second study is a very interesting one, a little bit ambitious as well, microsatellite instability prediction from routine histology slides, which is something which usually pathologists would not do from the routine slide. They would require additional dyes or additional stains to understand this kind of subtype, which is actually very important biomarker for immunotherapy selection. And last bit of my talk is about the recent shift from the frontier AI, how from deep learning we are moving towards more. Deep learning was about point solutions. We require for every downstream task, for every prediction task, we require a new model. But nowadays we are living in AI era where we are developing platforms. So just develop one big model and you can develop a lots of solution on top of that very quickly and efficiently. So in my first case study, we have been working on 2 different approaches. In one of the approach, we developed with a weakly supervised technique, like we provide computers with the pair of images and the diagnosis during the training. And in another Iguana, it was led by my colleague Simon Graham. He was trying to first learn from pathologists what they would be looking in the slide, and they will annotate it and then develop a computer algorithm that would first gather all the constructs that are required by the pathologist. They will develop computer algorithm to learn that and then build on top of that. So pre-screening here refers to developing an algorithm which can screen very high volume of data, colon biopsies, where mostly 30 to 40% of them are normal cases. So before those normal cases are viewed by, or even all the cases viewed by the pathologist, AI is run on it for pre-screening to tell us that which are more likely to be malignant, so that they can quickly send to the pathologist for review, and which are short normals which can be filtered out or maybe can be deprioritized. And just these are two different approaches, which I have already explained. So the workflow here is considering two key objectives here. So first is the safety, so sensitivity first. So we have selected very high sensitivity as an algorithmic choice, so that we do not miss any abnormal case to be flagged as normal or to be labeled as normal. And secondly, workload efficiency or reduction. If we are able to reduce the normal biopsy screening load from pathologists, their time could be spent on something which is more important. So what we found that we have selected 99% sensitivity, and both of the algorithms were surprisingly hitting the same target. Like they were able to automatically select 56% of the normal biopsies correctly. That means half of the pathologist load can be shared with AI. And there were very interesting flags from the AI algorithms, for example, which were about some diagnostic mistakes from the hospital's data, from the reports. So like if we see at this case, this one is a diagnostic category error. So in the diagnostic report, verified diagnostic report, this was said as normal, but it should have been flagged as something early cancer related. This is my second case study where people have been working on this area to predict microsatellite instability or other genomic biomarkers from routine tissue images. And initially it was based on pre-screening, but very recently new studies came. Initially it was more prediction, and now they are trying pre-screening so that they can select some of the cases based on AI, and they can avoid like costly lab tests for those cases. And recently, more about recent models. We have tried a recent model on it, which is based on foundation model. All these ChatGPT are based on GPT. GPT is a foundation model. ChatGPT is a chatbot on top of foundation model. So actual mind of the ChatGPT is a foundation model. So a foundation model quickly is a different story than the deep learning. It works with like scale and diversity. You put a lot of data during the training. For example, in the deep learning era, we have been looking at 1,000 cases, 500 whole slide images, 2,000 whole slide images. But now these models are trained on millions of whole slide images from multiple hospitals and all different organs. And they are trained in unsupervised way, like they learn from the data itself. And finally, once a model is trained, you can then retrain it very efficiently for any downstream task, for example, diagnosis, prognosis, stratification of any kind. So that is one of the bit, which was the reason why deep learning could not deliver us something reliable for the clinic, because they were very specific and they were trained on supervised way. But these foundation models are trained on diverse data and trained in an automated way, so they are learning the representation first and then solving the task. They are more likely to develop something which can be clinically deployed. And that quick system that enables this foundation model to be a clinical system is adaptation. in adaptation, control comes back to the pathologist. You can select your data, you can select the task that you want to use for this foundation model, and you can evaluate it at your own. This is the recent study that we conducted at Prince Sattam with our local researchers. We tried to use these latest foundation models to see how they can, how good they are in predicting or maybe enable us for pre-screening of microsatellite instability. So we found that we trained the model on US cohort and we tested it on US cohort as well as the Korean cohorts, and we found that one of the promise of generalizability, like model trained on the data would behave similar to another data may come from another hospital or may come from another demographic. It will be performing similarly, and that is what we have found. And this shows a potential of pre-screening. For example, 40% of the lab test PCR or NGS tests can be avoided if we can successfully deploy this kind of model. So this is my last slide. I went a little bit quick just to catch it on time. So this is the pathologist global penetration. And this part is Saudi Arabia. So we are like rest of the world, Saudi Arabia is also lacking in human pathologists. So 1 to 7 different sources report different number for 1 million population. So pathologists are really the limited asset worldwide. So the real question now for everyone, maybe I would like to hear from you as well, that and everybody is waiting for that, will AI be able to help us in this area? And I hope that Saudi Arabia, with its Vision 2030, is the leader, particularly to move AI for the pathologist in the clinic. Thank you very much for your time.